Thanks a lot. It's my honor to present in here. And my name is Ningyu Zhang from the Institute of Mechanics in China. And my total of my study is Pore-based prediction of crack initial life in very high cycle fatigue. And I will introduce from the following three parts. And for the first part is the background. For the traditional manufacturing, it's difficult to meet the requirements of special shaped components. Therefore, additive manufacturing can reduce the production with the requirements of ensuring the surface quality and the dimensional accuracy. Therefore, laser pulse bed fusion is one of the most widely applied technologies to produce critical components in many fields. But at the same time, the defects will result in more uncertainty in fatigue performance. And through the optimization of the process and the manufacturing and the post-up treatments, the defects like micro cracks, inclusions, surface roughness, and lack of fusions can be well eliminated, but pores cannot be entirely eliminated due to the rapid cooling speed, which will cause gas cannot escape from the as-built component in time. Therefore, it is critical to further study the influence of pores on the fatigue performance. For the fatigue performance, fatigue life is one of the most strict index to evaluate. But for the traditional fatigue life prediction models like stress strain, fracture mechanics, energy, and damage accumulation-based methods, which all need a large number of experiments to fit the material parameters to get more accurate. But also, they are always only suitable for the prediction of low cycle and high cycle fatigue life. But in the very high cycle fatigue, which corresponding to the failure cycle exceeds 10 million cycles, we expect a larger area due to the different dominant factors in crack initial and crack growth stages. Therefore, in this study, a pore-based prediction of crack initial life in very high cycle fatigue is proposed. Second is about the crack initial life prediction model and the corresponding results. The investigated material of this study is alum silicon tin magnesium, and the corresponding chemical composition and the manufacturing parameters are listed here. Then, firstly, the micro CT technology is applied to conduct the defect characterization. The porosity is measured of percent 0.33, and the distribution of the pore is equivalent diamond, and the sphericity follow the log normal and the Gauss normal distribution respectively. And then EBSD is applied to conduct the microstructure characterization. The microstructure shows a weak texture, and the distribution of the grain size follow log normal distributions, and most of are less than 2.44 micrometers. Specimens are then conducted with the ultrasonic fatigue test with a frequency of 20,000 Hertz. And the results of the stress and life curves and different stress ratios are plotted here. It can be found that the position of failure transferred from the surface to the interior near the fatigue endurance limits corresponding to the failure cycle of 10 million cycles. Then the fractography observations show that all specimens fail due to fatigue crack initial from pores, and it can also found that special radiating ridges can exist near the crack initial position. Therefore, in very high cycle fatigue, the majority of fatigue life is consumed in the crack initial life, and in a crack initial life, it mainly consumed in initial crack initial and early crack growth stages. The following is about the flowchart of crack initial life prediction model in this study. For step one is generation of pores and grains in a cell according to the previous microstructure and defects characterization. And step B is calculating initial crack initial life of all pores, and then the minimum initial crack initial life serve as the critical defects, and the corresponding grain size serve as the input to the step C to predict the early crack growth life and the crack initial life. As for initial crack initial life models, we adopt Chan's model modified kinetic and mirrors dislocations models by introducing the Taylor factor to transfer the micro model to macro model. And due to the stress concentration near the pore, which will cause the local stress to be higher than the applied stress. Therefore, in this study, the average local stress is adopted, and in many studies, the pore is always equivalent to circular. The morphology and the position are not considered in this study. These two cases are taken into account. Therefore, the stress concentration factors and the corresponding radiation convention need to be modified. For the maximum stress concentration, the finite element method is applied in this model. The inclination means the angle between the major axes of the pore and the loading directions. And it can be from the simulated results that the maximum stress concentration shows an increase with the inclination, and only the position of the maximum stress concentration factor of a pore need to be taken into account. Then the relationship between pore inclination, position, roundness, and the maximum stress concentration can be obtained by fitting the result of the fitted results. The obtained equation are listed here for eta equal 1 and 1.25 corresponding to the internal and the surface pores respectively. And the key initial equals 2.81 and the key and 3.03 corresponding to the internal and the surface circular pores respectively. And then for the position of the maximum stress concentration factor, the Petal proposed a model of the circumferential stress along the pore edge in polar coordinates. But in this model, the inclination is not considered. When the inclination is taken into account, it can be obtained that the applied stress decomposition along the inclination, it can be about the two equivalent models, and the circumferential stress considering the inclination can be obtained by the superposition of the stress field of the equivalent models without inclination. Then the radial current corresponding to the position of the maximum stress concentration factors can be obtained by stress decomposition along the loading directions. And the position of the maximum decomposition stress along the loading directions about the Phi-max, and then the corresponding radial convention can be obtained. Therefore, the average local stress can be modified by considering the pore roundness, inclination, and the location. And then it is substituted into the chance model to predict the initial crack initial life. And for the early crack growth life model, we adopt Sham's dislocation-based small fatigue crack growth model. The crack tip opening displacements can be obtained by integration of the dislocation density field function proposed by BCS model. And then integration from initial crack size to the rough area size, we can get the early crack growth life. And then the initial life can be obtained by adding the life consumed in the formation of the initial crack and the early crack growth in rough area. About steps in order to obtain the crack initial life probability distribution, the above steps are cycled sufficient times. And then after per cycle, the data storage and the statistics are conducted. After about 800 cycles, the fatigue life probability distribution can be obtained. It can be observed that the fatigue life probability distribution all follow log normal distributions at different stress ratios and the loading conditions. And it also become more scattered as the load decrease in the very high cycle regimes. Then the comparison of %95 confidence intervals for the fatigue life probability distributions with the experimental results shows the predict 95% confidence intervals for the stress ratio of 0 and -1 are conservatively when the failure cycles exceeds 100 million cycles. about the consecutive results of the point B and point C, the corresponding fracture surface are observed. It can be find that no obvious radiating ridges can be observed, and the region with granularly morphology called rough areas is observed, which means the occurrence of rough area can consume more fatigue life. And then ambient the shift of crack initial from initial position. The competition factors called CF is proposed to as a quantitative assessment of the tendency of crack initial from the surface of the interior by considering the influence of the average local stress and the grain size. When the CF is higher than 1, the crack tends to initial from surface pore, and when the CF is lower than 1, the crack tends to initial from internal pore. And when CF approach 1, the probability of surface and internal crack initial is identical. Also, after 800 cycles, the CF probability distribution can be obtained. The probability distribution of CF at different loading conditions all follow log normal distributions, and the variation of average CF with the decrease of loading are plotted. It can be obtained that the average CF values all approach 1 when the loading is close to the fatigue endurance limit and different stress ratios, which corresponding to the phenomenon of crack initial position shift from surface to the interior. The following is the conclusions. For the save time, I will not read it.
Okay.
Thanks for attention and welcome the question.